Uh,
Good evening. My name is Jack Galley. I'm here with my partners,
Kevin Martinez.
And Max Davidson.
and this is our Physics 212 project number 2. Start things off, some background information for project 2. Our group has decided to do the massive ropes or ropes with a constant mass density. With this task, we are tasked with designing a model that can be applied to a sled being pulled on a frictionless surface or a pulley system that uses a massive rope. And this massive rope completely changes how we looked at our old model, because now we have to consider how the mass of the rope affects the force. And some of the limitations that's going to come with this is that, well, with the new model, it was the ideal rope, and that is just plain unrealistic because we know ropes have mass. But as we move towards this newer adapted model, we have to take into account that this model doesn't apply elasticity of the rope, which is also an unrealistic guess or uh, unrealistic unrealistic guess. So moving into our adapted model, we're starting with the old model, and understanding the old model is key to understanding how we have made this adapted model. And to start, it is summed up by saying on a frictionless surface with an ideal rope, a force that is applied is going to accelerate the mass that the force of tension is pulling on. And so some of the relevant models and equations for this is, of course, force of tension is equal to mass times acceleration. And this is just because when we pull on the rope, we're creating a force of tension. And because we're on a frictionless surface, there is no friction to stop it. So whatever force, even if it's a 1 Newton force, then we're going to accelerate the mass so much. And so force of tension applied causes the block to accelerate, and then Newton's third law pair at the point of contact between the rope and the block. And this is important because saying that third law pair exists just says that when we pull on it, the rope is pulling on the block, and then at the point of contact of the rope and the block is pulling back. So we actually pull the block towards us.
For our adapted new model, we have to take into account the effects of gravity on the rope. So the main area of conflict between our ideal model and our real model we are attempting to build is the weight of the rope and the force of gravity that is acting on each point of the rope. However, we still make a simplifying assumption that gravity will act on the center of mass, which can be calculated and determined. Also, we know that if a rope with some mass mr, we need to exert some force on the rope to pull it and get it under tension. As you can see in the first diagram, there's going to be some slack in the rope initially at the center of mass due to the force of gravity acting on the center of mass of the rope. Therefore, we need to pull the rope at some angle theta to exert enough force to lift the rope in the y direction, and this will continue to happen until we have lifted the entire rope and it is tight and under complete tension. Some relevant models and equations for determining how gravity acts on the rope. From Newton's second law, we have the base force equation of force is equal to mass times acceleration. And the center of mass formula for a continuous object, where the center of mass is equal to 1 over the total mass times the integral of x dm over the length of the rope. Here we are using linear mass density, but this can also be applied to surface mass density and volumetric mass density. The x value within the integral will change based on the object being calculated for in either surface mass density or volumetric density. For the linear mass density, we have lambda is equal to dm over dx, or the change in mass over the change in distance. And surface mass density for sigma is dm over dA, where dA is the change in the surface area. And volumetric mass density, or rho, is dm over dV, where dV is the change in the volume of the object. You can then rearrange and solve for dm with the linear mass density equation for this example and substitute it into the center of mass equation to get the center of mass is equal to 1 divided by the total mass times the integral over the length of the rope of lambda times x dx. And when you solve that out, you can find the center of mass of the rope. For an adaptive model, using the pulley, with a pulley model, with an ideal rope, we move away from a system of constant masses and constant tension to a force of tension dependent on the mass of the rope, where the mass is dependent on time itself. And unless the pulley is in equilibrium, if not, the force of tension will increase because as the mass of the rope is pulled to one side, that side concurrently gets heavier and applies a greater force because of the increase in mass. And this is how we'll end up with getting differential equations within our force calculations. On the left, you can see that the pulley has two equal masses on both sides hanging at a equal level. So we have a net force of 0 because the mass of the rope on both sides is also going to cancel out. So there should be no net acceleration unless some force is acted upon the pulley. However, on the right, you can see that the mass on the left is hanging further down than the mass on the right. Or sorry, the mass on the right is hanging further down than the mass on the left. And because of that, you have more rope. So now you have a increased mass on the right. Additional relevant equations is equations for an object system, including the rope. So you'll have the force is equal to mass times acceleration, where the total mass is equal to the mass of the object being pulled. In this case, it will be a sled plus the mass of the rope. But the mass of the rope is equal to x of t times lambda, where x of t is a function of the length of the rope over time. So then you have your total mass is equal to the mass of the object plus x of t times lambda. And then you can plug that into your force equation to get the mass of the object plus the mass x of t times lambda, all of that times the acceleration to determine your new force.
Okay, so now that we have a model established, we can look at how this model can be used to describe some real-world examples. The first system we chose to look at was pulling a sled across a frictionless surface with a massive rope that has a constant mass density. In this scenario, we are standing stationary and pulling the rope towards us, and we're dropping the slack as we go. This will cause the mass of the system to vary over time. So if we are pulling with a constant acceleration, the tension force needed will also decrease over time. We can see this in the equations that I listed. The mass of the system is found by adding the mass of the sled to the mass of the rope, and which is the mass density times the length of the rope. Multiplying this by acceleration describes the tension in the rope. You can see in our two diagrams, the situation on the left, we have the full length of the rope. So we're adding that mass of the rope to the sled times acceleration to find tension. But then once we've pulled for some amount of time, we only have half the rope, so that tension is going to be less. The second example we chose to take a look at was two equal masses connected by a massive rope over a massless pulley. This is a system where we can kind of imagine how it would behave intuitively, but if we apply our old model, the math doesn't support what we can expect to see in real life. With our old model, the blocks can be in equilibrium at any point because the tension forces are only taking into account the mass on the other end of the rope. But now if we switch to the new model, we have to take into account how much rope is on each side of the pulley. So if one block starts lower, like in the diagram on the left, the extra mass of the rope will cause the left block to fall. And this lines up more with what we'd expect to see in reality. Okay, so let's talk about why our models make sense. First of all, it's important to understand that it makes sense to have two different models. There's situations where we don't need to take into account the mass of the rope, but not every rope we encounter has negligible mass. And when the rope is heavier, it's going to make a difference. And by adapting this new model to systems we have previously worked with, we can understand how this extra mass is going to interact with the systems. And we can also model systems that more closely resemble what we could expect to interact with in real life. During this project, we did some research, and we found these two good textbooks that helped us understand how the massive ropes are going to interact, and we found these very helpful. And that's what we have for you. Thank you.